All right, so we're going to do a very brief video on entropy, and we'll just start because it actually has a much more fancy name than just entropy. It's called the second law of thermodynamics. Now, what it essentially says that if you go in one direction, you can't go back in the other direction. Actually, it should have been like this. If you go in one direction, you cannot go back in the other direction. So if you put two reactants together, they automatically on their own turn to products, they will not reform the reactants at all. Now, that word spontaneous, the AP board decided they didn't like anymore. So instead of saying something being spontaneous, they now use the term thermodynamically favorable. So if a reaction actually goes on its own, in other words, we don't push it, we don't heat things up, we just put things together and we're like, all right, let's see what happens. If that happens, they say that the reaction is thermodynamically favorable or spontaneous. Now, spontaneous kind of implies to us sometimes that it's very fast, but spontaneous reaction can be really, really fast or really, really slow. As long as the reactants proceed towards the products, a reaction is considered spontaneous. And the other thing you need to be aware of is this. Thermodynamics, what we're going to talk about right now, it will tell us whether a reaction will go, but it will never tell us how fast the reaction will go. So, for example, carbon turning into diamond, that is spontaneous. It means it will happen on its own, but it takes a long time. Like, I would kind of be clever here, but it's actually taking thousands of years. Some spontaneous examples would be rust. I showed you an example of this. I mean, no one's ever going to see a car like this and go, you know what? Just give it time, man. It'll eventually become new again. That just never is going to happen. So what I'm going to do right now is we're going to define entropy. And since we already know that the E is taken for us, entropy has the symbol S, right? And we're going to use it just like we do other variables. We're going to talk about S with the little degree symbol, which means that it is under standard conditions. And we're going to talk about change in S a lot, just like we did before. So entropy is disorder. So the greater the disorder you have, the greater your entropy is. Now, I'm trying to get my screen to scroll down, but it does not want to scroll. There we go. So whenever you get a chance, whenever anything gets a chance, it'll always go towards more disorder. So if you have a bunch of particles over here on this side like this sitting here, they will, and you have nothing over here, if you open it up, they'll automatically always go towards where there is less disorder and make it more disordered. Now, I was going to go through a whole bunch of these and talk about microstates, but I don't really think that the APA board is going to talk about that at all. So you might want to briefly look at table 17.1 and how it talks about entropy in there, just to have an idea. But the second law of thermodynamics says that everything goes, that anything that's spontaneous in one direction can't be in any other. The third law says that we actually define zero entropy. So we say that if we're at 0 Kelvin, we have zero entropy. In other words, that's the spot where we have a solid crystal, which is the most, the least entropy thing you could ever have, and we have a temperature that is the lowest possible temperature. Now, what you should be aware of is this. These four things right here are incredibly important. So whenever you're comparing the entropy of two things, liquids have a higher entropy than solids, gases have a higher entropy than liquids. If you ever have something that's in the solution, it's kind of like being in a liquid, so it's going to have a higher entropy than solids. And if you ever have two of something, it's going to have a higher entropy than one of that thing. Now, what we can do, and this is crazy, we can actually look at any equation that's given us, and we can determine what the sign is for entropy. Because remember, sign indicates direction. So if we have this, if we have our change in entropy is positive for a reaction, that means that our reaction is more disordered. If our reaction has a negative entropy, it means that it has less disorder. Now, you can be a wordsmith and go, oh yeah, less disordered is the same thing as more ordered, and you'd be right. But I want to use the term disorder always so you don't accidentally mix these things around. So let's take a look at this, and all we're going to try to do is determine whether or not the entropy is positive or negative from the products compared to the reactants. So we're going to compare our product side here. If you take a look here, do you see we have 2 moles of gas on our products side? That was supposed to be an S, but it became a G. 2 moles of gas on the product side. On the reactant side, we have 1 mole of gas right here, and we have 3 moles of gas right here. So altogether on this side, we have 4 moles of gas, and on this side, we have 2 moles of gas. And anytime you go from more stuff to less stuff, you become less disordered. So our change in entropy for this reaction would be negative. We're becoming less disordered. Now let's take a look at this. Here we have 2 moles of gas on this side. Again, if you're wondering how we're getting this, we're getting it from the coefficients, right? And over this side, we have 2 moles of gas here and 1 mole of gas here. Again, very similar to the previous problem, we're going from 3 moles of gas to 2 moles of gas, so our change in entropy is negative. Now, what happens if we look at something like this? Do you see how we have here, we have 4 moles, but this is of liquid. So understand something here. When we're comparing things, gases are extraordinarily more disordered than liquids, and liquids are moderately more disordered than solids. Aqueous kind of fits in here. So when you're comparing a gas to a liquid or a solid, the gas's disorder or entropy is so much greater that 1 mole of a gas is equivalent to many, many moles of solid or liquid in terms of disorder. So this 4, they like putting on here because they're hoping that some poor waif of a student might not grasp or might not understand that that they're dealing with a liquid. So here we have 4 moles of a liquid and we have 2 moles of a gas. On this side, we have 2 moles of a gas here, and we have 3 moles of a gas here. So we have 5 moles of gas altogether on this side. And on this side, we have 2 moles of a gas. Yeah. We have also 4 moles of a liquid. But the gases, if you have gases, that's the only thing you compare. It's kind of like, again, what we said with intermolecular forces. If you have hydrogen bonding, you don't really talk about London dispersion forces. So in this case here, yet again, we're having a change in disorder that is negative. Now, I've just given you 3 examples, and all 3 examples have our disorder becoming negative. That does not mean that the disorder is always negative. That just happens. In fact, nature likes to go to modes of disorder. So given a choice, a reaction will always say, yes, please, I would like to be more disordered, because it's easier. So whenever we're dealing with disorder from here on out, just realize that even though we think that things would like to be more ordered, they really don't, because it's easier to become disordered. Now, this reaction right here, this is exactly the same reaction. If you want to remember, we could have done this exact same reaction, and on top of this, couldn't we have change in H and change in H and change in H? Because isn't this exactly the same formula that we used before? That's replacing this, right? So the change in enthalpy of a reaction is equal to the enthalpy of the products minus the sum of the enthalpy of the reactants. Same thing with entropy. So guess what? We can do the same thing with reactions, and we can look them up in a table. So the table at the back of the book, the appendix, it has a glossary or an appendix that has entropies of everything. But, and here's something that's incredibly important. The value they give you, and I don't know why they do it, I do actually know, because the amount of entropy, the units for entropy are pretty small, they're in joules, is typically given in joules. That's problematic because our enthalpies and everything else is given in kilojoules. So if you ever have a problem, and we're going to see those right away, where you have change in S and you have change in H in a problem, this will have units of joules, this will have units of kilojoules. You've got to convert to kilojoules because everything is done in kilojoules. I would normally do a few examples here, but again, I want you to just be aware of this, and we may practice on this in a little bit. Hopefully it's been helpful. I'll talk to you soon.